Let's get started. Thanks everyone for joining. It's been kind of fun doing these webinars and getting the kind of growing the number of people that know about each other. I look forward to when we can all be back in a room together and get the networking side going a little bit more. But definitely have a look at some of the chat participants, and there's some really cool people in the group. All of y'all are here because you're interested in data and improving the way we do our business. We all come at it from slightly different directions, and that's kind of been the inspiration for this series of expanding the toolkit of tools that we use on a daily basis, or think of when we want to solve our own problems of automation or analysis. Last week we had Mark Barrich, who showed us an introduction to Amazon Web Services, which they'd used as processing power for Q engineering. This week we have Thomas Martin talking about Google Colab as a coding environment. He's got an example of Python. If you saw in either the email that we sent out or on LinkedIn or in the chat window, there is a link to a GitHub repository, which you can download and upload into your Google Drive. And you can follow along and kind of use it as a practice template to see, kind of have your experience or try something out in Colab and follow along with Thomas as he presents. And next week, we're going to have Mark Ballard talking about SQL. Thomas is on. We're about to hand over control on the screen to him. He's a PhD student at Mines with a lot of experience in electromagnetics and geophysics. And I actually don't know a lot about what his thesis, his PhD focus is, but I'm excited for him to help us all understand Colab a little bit better. And he is involved with Matt Bauer on some of the education, trying to help the community understand and use Python a little more. So he'll probably mention that again, but you've seen his name around as a training source. And with that, thanks everyone for joining. If, as ever, if you've just come to us as your first time seeing this group, please feel free to send Mindy Stone or I. We'll include you on future emails or follow along on LinkedIn. And that's it. Take it away, Thomas.
Cool. Can you hear me? Everything's good?
Yeah.
Okay, awesome. So here is the GitHub link I just sent to everyone. Don't worry about the install, or you could do this after the video. But there's some small instructions used with Colab that I'm going to go over with now. The biggest thing is that you just want to clone or download. You do download the zip, and then you unzip the folder and drop it into your Google Drive. And so once you're in your Google Drive and you've dragged over the Denver data folder and you click on it, you should see some CSVs, a LAS file, awesome plot, and then 2 IPynib files. So if you've used Jupyter notebooks, this is the same file type as a Jupyter notebook. And so if you right click it or double click it, you can do open with Google Colab, or if you haven't installed this yet, you can do connect more apps, search for it, and then install it here. But for me, I already have it installed. But again, after the call, if you have any questions on how to get started, feel free to send me a ping. Okay, so this is a Jupyter notebook, pretty much. And so compared to normal Python scripts, there's cells with text, and then there's cells with code. So they're really nice for sharing ideas or comments or deep thoughts, or like if you're trying to communicate it to a team member or research group or something else. It's probably not the best environment for peer production. You know, if you're trying to do this 10,000 times, it's probably faster to do it in a normal Python script. But I like these for iterating, communicating, and doing smaller-ish research projects than putting into your like daily, use. So the first tricky thing, you have to mount Colab to your Google Drive. So for me, it's already mounted because I just ran through this right before. But when you run a Google Colab notebook, it runs like in its own free space. You have to connect it to your Google Drive. That is just to protect your data. So you have to explicitly tell it, yes, go search through my Google Drive to find my guacamole recipes, 8th grade photos, and anything else you keep in your Google Drive. And so until that happens, it won't see any files, even if it's in the same folder. Then I just do some quick Unix commands to just navigate to that folder. So again, these aren't Pythonic, but these are really handy to navigate around folder structures in any Unix system. One thing, if you're following along and you do the ls, which is the list command, you should see the contents of that folder. So there should be 2 IPynib, a LAS file, a couple CSVs, and a PDF. If this is all brand new to you and you're like, what is Unix? What are you doing? There's a cheat sheet that's hyperlinked here. And it's just a really good way to navigate around, remove folders, open folders, unzip and zip stuff up. Okay, so finally, let's get to some Python. And so while doing 2 + 2 is not mind-blowing, doing it without a local Python install is. So instead of suffering through 30 minutes to 4 hours of getting Anaconda on your local machine, you can now run Python in the cloud anywhere with internet connection. The other advantage of this is you don't need administrator rights. You could do it on a Chromebook. You could do it on an iPad. All you need is a internet browser in Google Colab. So as far as portability, it's awesome. And again, there's some basic math built into Python. This isn't a basic Python course. There's a lot of resources for that. And I'm sure if you're familiar with MATLAB or other languages, some of this will look very familiar. One thing in a code cell, if you want to do a comment, it's a hashtag, not a % or other stuff. One different thing is that it indexes 0, 1, 2, 3, not 1, 2, 3. So with this variable C, equals, the string rad, if I get the 0th thing, it's going to be R. If I get the first thing, it's going to be A. So that's just one thing that might be a change from other languages that you're used to. Again, there's a whole Coursera, edX's, how to automate the boring stuff. There's a lot of different entry-level Python stuff to learn how to do for loops, functions, or the RMAT class with Matt Bauer and I. So that's not going to be today. So a big thing is, if you're familiar with MATLAB, there's these things called toolboxes. In Python, they're called packages. In Colab, you can import the most used ones directly. Because matplotlib is used by like thousands of people per day, we don't have to install it. We can just import it. Same with pandas and numpy. So pandas is like a data storage package, and numpy is like a math package. So one thing we are going to install, because we're all geoscientists, is this thing called LAS.io. So it's a LAS file reader and writer. I love this package. I use it every day. It's developed on a weekly basis. A new version comes out, and it's has been good with every North American LAS file that I've ever used. And if there's an LAS file that you can't use, send it to the developer and they'll fix it. So last couple weeks ago, there's a guy from the UK that had like hundreds of inches as the unit. And it was for like uranium exploration cores in like the 70s. And so the depths were massive. And they were able to figure it out and fix it up in a couple of days. So again, if you use LAS files, want to read them, want to write them, this is the package to use. Then even after you install it, you just have to import it still. So these are two different things. Again, above, we just imported it, but if you're using more specialized stuff, you have to install then import. So there's hundreds of these Python packages. Not all of them will work with Colab. Colab's going to be more designed for mainstream scientific software. So anything TensorFlow, SciPy, scikit-learn, anything that everyone will use, especially data science, will use. I would say the more obscure academic code you want to import, the more trouble you might have to have. So, okay, so now I kind of zipped through the first part. Now we're going to get to the part that we're all interested in because we're all subsurface scientists. So we're going to, from that LASIO package, we're going to use the read function, read in that LAS file in the folder and call it this LAS object. Okay. And then if you just want to inspect the curves from that, you do las.curves, and this will actually has a ton of curves. So, you know, SP, tension, gamma ray, all these resistivity curves. But from this one object, you can call a whole bunch of different things. So if you do las dot, you can find a bunch of stuff like las.well. So this will be like the header here. So the company, this is Anadarko well, here's the name, here's the field, the county, the state. And so all the information that's normally stored in a LAS file, both in the header and the curve names, the units, all of that stuff, you can now call it from this LAS object. So another thing that you can do is that you can turn the data into a data frame. And so the data frame, think of it almost like a spreadsheet on superpowers, but we see depth here, we see all the curve names here. And then, so if you just want to play with the data and work with the, you know, well logs, you can do it as a pandas data frame. The other thing, this was a big hit in the RMAG class, is that if you just want to read in a LAS file and write it out as a CSV instead of manually cutting and pasting the header out, you can do that in one line. So I know some people here probably use Spotfire, or maybe it's easier to import it in, you know, your Patrol model or something like that. But if you just want to read in a LAS file and read it out as a CSV, you can do that in three lines of code. The other nice thing you can do once it's in a data frame, you can do data.describe, and this will pull up some stats for each column or each curve in our case. So for AHO10, so this is a shallow resistivity tool, we have the count, we have the mean, the standard deviation of that mean, the minimum, the maximum, and a couple of percentiles. And so even if you scroll through, you can do a quick QC of your well information this way. You know, if you had a negative bit size, that might be concerning, or a negative gamma ray, you might want to adjust that. So this is a really quick way to look at the entire health of your curves without doing too many steps. Again, I don't promise to be a petrophysicist. So you know, some of you here probably know better than me of what's best to do. If you want to export this little data.describe table that we have here as a CSV, you could do that again in another line. One thing is too is that one thing else you can do is pull these min and max values directly. So if you want to cycle through a bunch of logs, and you don't want to hand do the minimum or the maximum for the gamma ray for your log norm lunch and learn, that's tomorrow, you can just call, you know, the minimum of that curve. or the maximum of that curve, and then it will automatically update. So for us, let's make a low gamma ray and a high gamma ray cutoff. And so for this, I have a low gamma ray variable, low GR equals data, which is our data frame, dot GR, which is a column name or the gamma ray curve. And I'm going to use the quantile function and then set the cutoff at 0.2. You can change this cutoff to whatever you want it to be. It's the same thing for my high resistivity variable. It's going to be data.AHO90, which is the deep resistivity curve for this well. I'm going to look stuff for in the 95th percentile of resistivity. Or if we think that's too high, you can pull it down to 90. Again, you can mess around with this, and you can, make these high and low cutoffs. You can do them static. You can do other math. You can. The world is your oyster as far as making these numbers be whatever you want them to be. So now, using this tool or using Python, we imported matplotlib earlier. And I apologize for not going through line by line, but just for our time here, I'd rather have a more lively discussion afterward. And if there's specific questions about specific cells, I'm happy to go over that after this course or another day. But we can plot, we can make a scatter plot comparing gamma ray versus deep resistivity. We set the color to blue and the alpha, which is how transparent it is, to 0.3. We did the Y scale and the log axis. We turned the grid on and we put 2 axis labels. There's a lot of different ways to make these matplotlib figures. This is a relatively basic way to do it. If you're used to MATLAB, it should feel somewhat familiar. But again, you can make these cross plots a million different ways. You can set the marker color to be another variable. You can set the marker size to another variable. And so any sort of petrophysical cross plot that you're looking to do, you can do them, in 6 lines of code here. If we just want to make a histogram, so here we're going to do plt.hist. And so this is going to be data.gr.values. So what I'm saying here is that in the data frame of the gamma ray curve, only the values of that, let's plot them with 20 bins. The color is G for green, and then some axis labels, and then you can get a histogram that you're looking for. If you think 20 is too many, you can change it to 10. If 100's more your style, you can change it to 100. So, okay, but what's probably more interesting to you is to plot the gamma ray as the curve like we've all seen in other software. So the only trick here is plt.plot. So it's gamma ray again, and then data versus data.index. And so on our data frame, the depth is the index. So then you can get a plot of your LAS file gamma ray curve in green. The other trick here, that I sometimes forget, is I'm setting the Y limit to go from 2000 to 0. So I'm flipping it. If I comment this out, how it normally plots is a well log in the air, which is probably not what you're looking for. Okay. The other thing we're going to do on this next plot is that we're going to set the title of the plot to be the name of the well. And so in that LES object, I'm going to ask the header in the well information section using the well name and just the value. And while this is more convoluted, then the well name for sure. This is kind of a bit nitpicky to make sure you're getting all the things that you need. But once you do this once, every new well log that you load, it will load in the well name for that well log. And so a lot of times with these Python tools, you're going to suffer a little bit more than doing it once. If you're doing it 5 times, 10 times, 20 times, it's definitely going to be saving you some time down the road. Okay, so these plots will look very similar to what we've seen before. I'm just going to show you the goods of here's our gamma ray plot. Here's our deep resistivity plot on the right. One of the changes here is that it's it's a log axis on the x-axis for the resistivity. And so how we did this is we made a figure. We made an overall title, which is the well name here. We made 2 subplots. So it's PLT subplot. And then this one we did the gamma, and then this one we did the both shallow and deep resistivity. It's kind of hard to see the shallow resistivity. Okay, and then now, since we have this nice plot of both gamma ray and deep resistivity, we're going to make a pay mapper variable. So you can do this in loops. You can do this as a function. This is simple enough that you can use it, using Pythonic nomenclature. So what I'm saying here is this variable we're calling pay mapper is that if data.gr.values, so if the gamma ray values are less than or equal to that low gamma ray cutoff that we made, and the data.deepResistivity.values is greater than or equal to high resistivity, make it be true. So this NP unique is just shows what are the unique variables in pay mapper. So we have a false and a true, which is what we're looking for. If you want to know how many falses and trues are in there, we can do a bin count. And so we have 19,035 falses and 1,500 trues. Again, your cutoffs might be a little bit different than mine, so your numbers might be a little bit off, but it's just an important way to QC this without looking at all 20,000 variables. Because one issue is if you take away this NP unique and you just show the pay mapper, all it shows is false. And so it's really hard to QC these really large variables visually. Okay, so now we have our pay flag variable, defined here. We have these nice plots of both gamma and deep resistivity here. Let's plot it all. So I'm going to run it and show you the goods and then go back here. So these are all on the same depth axis. So we have the deep resistivity here, the gamma ray here, and then our pay flag shown in red here. This pay flag's definitely probably a little bit heavy. You can play with those quantile cutoffs to get something that's probably a little bit more realistic. But this is a really quick way to visually inspect some LAS files completely free. So like the plot above, the only thing that we added here was a new subplot using the PLT fill between. And then we did the pay mapper variable against the data.index. So this is the depth. Then I set the color to red. Again, there's so many different ways you can mess with these plots as far as turning the grid on, changing the line sizes, the colors. You could do dots or dashes or anything else. But you can play with well logs, do some petrophysical stuff, all in the cloud, all for free. All right, and then I'm going to show you the next notebook. So the next notebook is 2_slider bar. And so one thing I've chatted with a couple people in the industry is people love their Spotfire licenses. And I asked my friends, what makes Spotfire so great? And I agree, it's a great visualization tool, but it's completely built on Python. So again, if this is your first notebook, you'll have to mount the drive. And then I'm already in there, so I'm getting some errors. And then I'm going to read in a Wyoming production CSV. So this should look familiar to a lot of you. You have the API here, you have the month, year, you have the oil, gas, and water barrels, and then days here. I think this is a gas well in the Greater Green River Basin, so there shouldn't be exciting oil plots here. I'm going to just quickly rename these columns. When working with Python or most Unix systems, it is possible to use, but it's kind of annoying to deal with spaces. And so we're just going to change the column names using the dataframe.rename function here. And let's look at what it looks like now. So again, the data is exactly the same. I just changed the column names to remove the space. So a quick plot of the oil production in this well looks like this. Again, this is just using matplotlib, and this is a normal Wyoming production CSV. And then one cool thing in Colab you can do, so if you want to share this with a friend, is you can hide the code behind the slider. So here's, I have a little if and else if statement, but a lot of people won't care about that. More people will care about this drop-down menu to pick the fluid type and using a slider to pick what you want to plot, and then making a little best fit line using sklearn. If you want to bring this in, you can. These fits aren't great. It's not a true decline curve tool. Sometimes it works, sometimes it doesn't. But I made it in like 10 minutes. So when you change the fluid type, you will also change the axes, and then you will also change the color of the plots. And so if these sort of dashboards and slider bars and drop-down menus, if that's exciting to you and your team, you can implement this stuff using Google Colab. I knew I kind of blew right through this. The main takeaways for me and kind of Matt's, the class that we taught at RMAG, is there's a lot of tools out there for free for subsurface geoscience data. And it doesn't take too long to get up and running, making these awesome plots, making your pay flag, doing some analyses you're already doing, and probably, other either packages with big license fees, or maybe you don't have access to because you're in between gigs and you still want to play around with all this great open data that we have. One thing I just want to go into before we hopefully have a little discussion about this and answer questions. It has been and always will be a data problem. A lot of times we talk about big data in oil and gas, but how much of that data is trapped in PDF reports or paper well files deep in the basement of your company? So, I think, data first is kind of where my vision is. A lot of people have asked on previous data drivers talks, what language should they learn? I think R is great from a statistical point of view. if you have nice and clean data. If you're working with subsurface data, there's so many packages written for reading and writing in Python. There's seismic readers and writers, there's DLSIO readers and writers, there's LAS readers and writers, there's ArcPy, and so there's a whole kind of geo ecosystem already in Python that would be really hard to recreate in R. And so if you're working with only production data or other more clean or economics data, I think R might be have some better tools. But if you're trying to use typical G&G subsurface data, I really recommend starting with Python. The other thing is not every problem requires high dollar machine learning, but usually every problem requires good data. I'll just touch on this last one a bit. Most smaller companies would probably be better served by hiring a part-time developer consultant to make some of these great tools compared to paying for some licenses. Your mileage might vary on this depending on your specific workflows, but if you're opening up a tech log license just to make a PNG of your well log, you could probably save 10 grand a year on that. So with this, I would love to open it up. I know I kind of blew through all of that, but it'd be great to get some two-way chat on this or deep thoughts or anything else that's on everyone's mind.
Awesome, thank you. I think just for a beginning, if anybody has questions or wants to chime in, feel free to unmute and ask away. And I'll sit back for a minute, and if nobody has questions, I'll ask.
Hey Thomas, Michael here.
Hey, what's up?
Hey, thanks a lot for this demo. It's great. So my question is actually about the Colab part of it. So say I make a Colab notebook and I want to start to collaborate with someone.
Yep.
Is it like Google Drive where if I send them my Google Doc or my Google Sheet, that if they start editing it, it will edit the file I'm also working on? Like a live collaboration? Or is there like I imagine there must be two ways to do it, right? But I couldn't figure that out the last time I was looking.
Yeah, there's this setting. I'm trying to find it. I don't really use it. I want to say it's like Lightning version where you have to like turn that on. It's not quite like Google Sheets, but I know that if I probably wouldn't count on that, but if you have a friend in Perth, Australia, and you work on it, and then you head home for the night, then he works on it, I think it will update those, but I don't think it's quite as good as like Google Sheets where you can see, where I could like see you type, and then I, write you funny notes when we do that. So, but I like
by
it.
default, if you share someone a notebook, they kind of just have their own notebook to play around in, and it doesn't affect your original file.
Yeah, so you have to dig into the settings to kind of have that two-way sharing. But you can, like, I could share an easier way to share this. Like, if I was using all synthetic data, I could just send you a link to only this notebook. Why I like doing it through GitHub with the folders is it's really hard to share the data and the notebook and have it all work. But when I send you
mount to your drive and stuff.
Yeah, exactly. But if I send you a GitHub with a folder that you just drag and drop into your Google Drive, all of that sort of meshing seems to work a lot better.
Awesome. Cool. Yeah, thanks a lot.
Yeah.
Thomas, can you show a little bit about how like data describe or your plots could be used adapted so that you don't have to show like the entire LAS file, but you select subsets? I think it's basically the basics of a little bit of how pandas work, and also, well, yeah, I think that'd be the main one, just so it's clear how things are going. Yeah, pandas, you can select subsets, and then the other part was on the gamma ray, when you created your new curve, your cutoff curve, can you explain how it recognized a depth Because you just kind of showed how you did the calculation, but it's not obvious how that depth transferred across so that when you plotted it knew where to put it.
Yeah, so I'll answer your questions in reverse just for ease of use. So, because I didn't change the index, and so when I make the sweet cutoff, so when I make this cutoff here, it's not the shape of PayMapper. So this is the same number of counts as the gamma array. So it will still put out a false if there's not a, because there's not a gamma ray measurement for this whole well, but there's still like a depth tick, and so it's doing false, 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 false here. So I don't have to feed it a depth. I'm just not changing the index.
So I guess for everybody, I'll point out. So the way, if you think about when you look at Excel and every row has a number and every column has a letter. The pandas, the way is that every row has a marker and that's the index. And here it's using depth as the index and it's pulling depth from the LAS file. And that's how Lassio is constructing the data side of the LAS file as this big array in the and then when he plots it or does a calculation or selects subsets, the depth automatically crosses over. And you can make that index. You could even have multiple wells and you want to incorporate together or unite for whatever analysis you're doing. So there's more flexibility there, of course, than just what's shown here. But I thought that was it's a neat thing to see how easy it is to keep track of depth when you're doing the math.
Yeah, and the one thing that I kind of go back and forth on is, do you have the depth track as a curve or do you keep the depth track as an index? Because you can make a new index in pandas, so just be 1, 2, 3, 0, 1, 2, 3, and then you just, when you make plots like here, I have data.gr, and here I have data.index. Instead of doing data.index, it just be data.depth. And so I kind of go back and forth. I almost like thinking of, I almost like putting, making the depth track its own curve, because that's how I think of it. But again, it's all the same. It's just depending on what's best for you. So one way you can kind of set upper and lower depth here, I can just do it here or on the slider bar intro might be an easier way to do it. I can open up the code. There we go. Okay. So here's a plot. Sorry, there's a lot of stuff going on. But what you do is that you just tell it, like on the slider one. So I have my min month slider, so that's variable. Then that's variable 1. Then max month slider. And so I'm plotting this on the index on df.index, so on the months, and then I'm indexing it from the min month to the max month. And so when I change the sliders, I'm changing those variables here. Is that getting at what you're, sorry, Kurt, if I'm not answering your question or.
Yeah, no, I think it definitely is. And for people that are unfamiliar, or this is like your first exposure to something in Python, like taking this code and playing with it and breaking it and fixing it, and you'll learn a lot. And when you have questions or are concerned, obviously ask people, or the amount of information that's available you can learn from understanding what, like the min month slider, when that value is changed, how that's affecting index, and what would happen if you put in a number that didn't match an index. What does that result in? And kind of playing with it, you'll learn an awful lot.
Yeah, so one thing I did here is that if I do, if the min month is greater than the max month, you get this error and doesn't plot. And so there's going to be a smarter way. So the top error, sorry for my scrolling, the top error is error, check min and max month. And so you can even write your own little error codes like, oh yeah, like this doesn't make any sense. But then when you put it back and press go, it all works. And so Python will let you do whatever you want. It's not a domain expert. So if you want to do something really silly, it gives you the power to do that.
I know, like somebody like Matt Belabridich has been doing some core work. There's that plotting in those depth flags that you're getting, or the depth ticks on the index for the plots that you were doing. Things like Petra can sometimes run into problems with inconsistent or erratic data density. Whereas here you can load core data straight in to join the Panda of your LES file and start doing plots of against log data and doing your, whether you want to build a machine learning tool or whatever. This is a great place to do things like that.
The other thing
sorry.
Yeah, go for it.
Another great thing with LAS.io is that with Colorado Oil and Gas, you can pull down the file just enough to grab everything off the header in the LAS file and shove it into MySQL with some of the tools that are in that LAS.io. It's just absolutely so powerful. You can get all of those statistics for all of those curves, and you don't have to store the entire file local because there's 57,000 of them. There's no reason to have that on your computer.
That's awesome.
The other thing you can do too, which I'm in the process of for my research, is the index on the depth steps on this. I'm just going to start new code. So the depth steps and feet are a little weird. And so if you want to get the same depth steps for, every well in your petrophysical study, you can linearly reinterpret all of this to be like every 10th of a foot or something. And so it's a really nice tool, even if you want to keep, what I've done with some LAS files is keep the same header, read in everything, redo the depth steps at every 10th of a foot, and then re-export that LAS file. Walter, you shouldn't have to change anything to the drive.mount as long as you drag and drop that whole folder over.
So you don't copy and paste. Oh, pardon.
Go for it, Walter. Sorry.
So you don't copy and paste the URL of your own like Google Drive homepage into that drive mount command?
It should work fine as long as you pasted it into your main part of your drive. So like for me, this Denver data
folder.
Yeah.
Everything else makes sense. It's funny, I have problems with the file path stuff sometimes. Tricky.
Yeah, mounting the drive is the most annoying part. Once you clear that hurdle, you're kind of home free. But I will agree that it's probably the least ideal part of this whole situation. So
for sure, but it's pretty quick after that, it looks like. I'm encouraged.
Good.
So Thomas, this is Ben Burke. So given you taught the February class in Jupyter Notebooks, and now you're using Colab. Are you have you pretty much moved on to Colab, or is there still value you see in certain situations for Jupyter Notebooks, or is it really just a matter of preference?
I think for some things, like for plotting or for some of that web scraping we did in the class, not everything will work in Colab. Colab's really good at the top 100 most basic things you can do, or top 1,000. But the more niche, the more specialized, especially with plotting stuff, it doesn't really like Cartopy. which I think we used in the class or some of the other things. And so I would say it's not perfect. So for me as a teaching tool, I like Colab, or as a sharing tool, I like Colab. I think if you're a professional developer, you should still probably have a normal Python install on your computer. The one nice thing about Colab is that you can do it from a Chromebook, from an iPad, from a 7-year-old Windows machine. As long as you have a modern browser, it's good. One nice thing why I was interested in Colab was they have Google Colab Pro. And so I paid $10 a month. And if I look here, this won't affect it for this notebook, but if I go to runtime, I could do change runtime type. I could do high RAM in GPU or TPU. So a GPU is a graphics card, and TPU is like the Google like TensorFlow cards. And so if you want to do intro machine learning stuff, but you don't have $1,000 graphics card, you can do all of that in the cloud for $10 a month. So this is really the big reason why I got really psyched on Google Colab, is that if you want to test the waters in machine learning, this is by far the cheapest way to do it and the easiest way to do it. Even if you just, 3 months is $30, and that's way cheaper than a $1,500 computer with a nice graphics card.
Thomas, quick question. It's Donnie Keeley here.
Hey.
If you wanted to run this, like if I wanted to run it at work, what would be the best way to go about that? I mean, because this is all running through like personal drives right now. Is there a corporate way to set this up, or?
The best way is you need to allow IT for you to upload stuff into Google Drive. And then the other thing is, I think that's really it. I've used this, so I just made a Google account for this, but I've also used it with like mine's email, which is through Gmail. So you just need a free Gmail account. And so even if you made a bunch of burner oil company _1 at gmail.com to do this stuff. But without you being able to upload and download stuff into Google Drive, I think it would really handicap the usability of some of these tools.
Right. I just didn't know if there's a corporate solution, because like uploading a bunch of IHS data to my personal Google Drive is not going to fly.
No, for sure. Yeah. And I would say if you want it to scale it more than a bunch of toy problems like that,
yeah.
Probably a local install of Jupyter is probably what would be better.
Okay. Thanks.
I haven't really explored the limits. The high RAM on Google Pro is like 28 gigs of RAM. And so that's pretty good. You can do, smaller field studies, probably not basin-wide scale. And I know the other thing is that if you can write it in this, you can write it in like Google Compute Cloud, and that's when you can turn on, 256 gigs of RAM with like 8 T100s if you really want to burn somebody's corporate credit card. So it really just depends on what scale you're looking at.
Yeah, I haven't gotten there yet.
Yeah, neither have I. So I'm really happy with the $10 a month for sure. So.
Hey Thomas, this is Nathan Brown. So when you're saying that this is better for more simplified processes, I'm going to assume that this isn't a good platform for anything that would require an environment or is especially finicky about its dependence and requirements.
Yeah, I think like I know that this can import like older versions of TensorFlow. I've used it for that, like TensorFlow 1.1 and 1.5. But again, I would say the more niche of workflows you're doing or packages that you're doing, the probably less and less the ability for this to work out of the box. Pandas and NumPy are used by, millions of people every day. They import, with zero error. And even LES.io imports extremely well. Cartopy is like a more niche plotting software that probably has hundreds to thousands of users. And that one breaks and requires a really insane way to install it that I didn't really want to go over with here. And so I think, yeah, I would just stress that the more weird it gets, the less likely it's going to work out of the box.
So on that note, Colab doesn't like support YML files or anything like that.
Not that I know of, and I think even if they did, if you have an exotic YML file, kind of no guarantee.
I'm not sure who it was earlier, but somebody was talking about looping through LAS headers, which is something that I've done a lot, although I've only worked with R. What kind of speed do you guys get with that, and what like size data sets have you done?
I've done like the entire open LES files from like the UK. So it's like hundreds to low thousands of LES files that they have. And I can loop through and load that in a whole data frame in minutes. So
Yeah,
it's
physics in it, and I can do the whole DJ basin, like run where I'm creating new LES files, so constructing new headers, and running the math of the petrophysics, and it's doing it. It's on on the order of, minutes to hours kind of thing.
Okay.
10,000 wells, 5,000 wells.
Can you do multi-processing with this Colab, or is that all local that you're working with?
I haven't looked at it. I don't think so.
If you have a GPU, you should be able to.
Yeah, I always the limit on my end is writing code, and so even if I have to wait 5 minutes, if I can get the code to work, I'm a happy camper. I think if I need to shrink loading in 5,000 wells from 3 minutes to a minute and a half, then I should probably call up a professional computer science grad and a bunch of weird geologists like myself.
Comment for Donnie that there's a little known, or I think it's a little known LAS.io feature that when you run that read command, lasio.read, you can pass to it an argument data equals false, and it won't read any of the log data. So it won't parse the whole file. It'll just parse the header portion, and that cuts a huge percentage of the time off of reading those.
Oh yeah, that would be nice. Thanks for the tip.
Well, thank you for doing that. That's awesome. I will point to one that we talked a lot about the AS reader, that little decline curve tool or play sandbox that he built is kind of neat. And there was I saw that David Fulford had built a repository or his toolbox for decline curve analysis is as another Python package that you can install, and it would be really fun to play with, kind of building a Colab notebook around his decline curve approach. I have a feeling you'd find you have something incredibly powerful really quickly. This is an awesome talk. I really appreciate it, and thanks for showing us all how to get started. If anybody wants more information, reach out to any of us or to kind of explore this more. Of course, there's more training available. If this is the kind of subject you'd like to see dived into further, or this kicks off ideas of things that we can do in the future, we're going to keep having events long after COVID, and we'd love to kind of start going more and more into the weeds of the avenues that you're most interested in. So please reach out if you'd either like to present or would like to hear more about something. Let me hear, I know, and we'll try and make it happen. Next week, we're going to talk about SQL. Thomas, thank you so much. This was great.
Yeah, thanks. This is just a small taste test of what you can do if you're really fired up on this stuff. There's a group called Software Underground that's having a free online conference this week. And I know Michael Hardy and others has made a really awesome like web tool for looking at these LES files as part of a hackathon. And so there's a lot of really cool stuff happening in the Python subsurface space. And so again, thanks for giving me the opportunity to give this a shout. And if you have any questions or comments, feel free to hit me up on Twitter or LinkedIn or anywhere else. So.
Thanks, Thomas.
Thank you.
Thank you.